Chapter 1: Einstein's Static Universe.
There is still taken into account the condition that at spatial infinity the potential phi tends toward a fixed limiting value. There is an analogous state of things in the theory of gravitation in general relativity. Here too we must supplement the differential equations by limiting conditions at spatial infinity if we really have to regard the universe as being of infinite spatial extent. In my treatment of the planetary problem, I chose these limiting conditions in the form of the following assumption. It is possible to select a system of reference so that at spatial infinity, all the gravitational potentials g mu nu become constant. But it is by no means evident a priori that we may lay down the same limiting conditions when we wish to take larger portions of the physical universe into consideration. In the following pages, the reflections will be given, which up to the present, I have made on this fundamentally important question.
After publishing dozens of articles on special relativity, Brownian motion, and mass energy equivalence, Albert Einstein accepted a position at the Prussian Academy of Sciences in Berlin in the spring of 1914. 3 months later, Germany declared war on France and Russia. Einstein found himself in poor health, financially strained, and living alone during World War I. Yet, despite exhaustion, illness, and isolation, he produced some of his most important breakthroughs, including the completion of general relativity. Just a few weeks after Einstein's publication, Karl Schwarzschild derived the first exact solution while serving on the Eastern Front. The Schwarzschild metric describes the geometry outside a non-rotating, spherically symmetric ball of mass, like a star or a planet. In its standard form, the line element is, and I'm not going to read these equations, by the way. If you're blind, I don't know, man, I'm sorry. Some of these I'm just not going to read. You'll just have to get somebody else to read them, but I will put them on the screen. Some of them are just going to be too long and arduous for me to read. But this is the Schwarzschild metric, where g is the gravitational constant, m is the mass, c is the speed of light, and r is the radial coordinate. The solution resolved several issues and is considered one of the most fundamental and foundational solutions of all time. Initially, the Schwarzschild solution was viewed as an astrophysical tool for modeling stars. But now the solution is equally known for its ability to define the radius of a black hole. The critical radius, Rs equals 2gm divided by c squared, or the Schwarzschild radius, is the radius of an object with enough mass so that its escape velocity is equal to the speed of light. Sadly, Karl passed away not long after his correspondence with Einstein. A year later, Einstein published Cosmological Considerations on the General Theory of Relativity. This solution begins with a spatially closed metric with a three-sphere of constant curvature radius capital R. So space is finite in volume but unbounded in extent. The line element is where x is the dimensionless radial angle and d omega squared is the usual solid angle term. He chose g subscript 44 equals 1 and g subscript 4i equals 0, keeping all coefficients independent of t. Matter appears as a pressure-free dust of uniform density ρ. To keep the dust in equilibrium, he modified the equations from 2, introducing the cosmological constant. Static balance then requires the equilibrium is neutral, but a slight increase in ρ causes collapse, while a slight decrease allows the cosmological constant to drive unlimited expansion. The delicate balance generated interest and curiosity in the role of the cosmological constant. Willem de Sitter presented a solution with a non-zero cosmological constant and ρ equals 0, which describes a universe empty of matter, but is still expanding due to the cosmological constant. This was a strange result that suggested that lambda did not need mass or energy. Theoretical developments like the instability of Einstein's universe, the cosmological constant, and the Friedmann equations provided enough novelty for a wide range of potential universes. Still, it was Hubble's discovery that solidified lambda cosmology as a legitimate theory in the minds of academics. There is a subtle nuance to the way the story developed that is rarely communicated in the literature. One of the main reasons that cosmological redshift is claimed to be evidence of expansion comes from the timing of George Lemaitre's 1927 paper. In that article, Lemaitre suggests that the universe is expanding as a means to explain the cosmological constant. He explicitly uses data from Hubble and Stromberg's lists to derive the rate of expansion. Lemaitre was attempting to use general relativity to explain the redshift. He wasn't predicting a redshift based on some other assumption. Hubble's work was published 2 years after Lemaitre, but the data was available for several years before publication. The community was also struggling to create a satisfying solution for cosmological scales. More importantly, there is an accurate meme present in all of these papers that persist in cosmology today. The title of his article was in French. Un univers homogène de masse constante et de rayons croissants redant compte de la vitesse radiale des nébuleuses extragalactiques, which translates to a homogeneous universe of constant mass and increasing radius, accounting for the radial velocity of extragalactic nebula. The chosen ensemble was a homogeneous universe of constant mass and is similar to Einstein's universe, as well as other formulations from that period. While these formulations sound reasonable enough, it is important to remember that mass density is a scale-dependent variable. It is literally impossible to construct a universe with a homogeneous mass density. In addition, if you force homogeneity as an unrealistic concept, the mass density is still radially dependent. Collapse or expand. Over a century has passed since these giants laid the foundations of cosmology, and while their contributions were significant, not much has changed since then. Lambda CDM remains the dominant cosmological model. It is still rooted in the FLRW metric and still uses homogeneity as a global property. Through its failures, the model has now evolved into a rather large collection of parameters, frameworks, and assumptions. Einstein introduced the cosmological constant as a repulsive force to balance gravity in his static universe. But its origins were never derived from fundamental physics. Today, the cosmological constant has been repurposed as dark energy, which accounts for the lion's share of the universe's total energy budget. Yet lambda remains at the heart of the biggest mystery in physics. At the heart of general relativity is the principle of general covariance, which states that the laws of physics must take the same mathematical form in all reference frames. General covariance is the engine of general relativity. In my mind, the way it works is that special relativity plus the equivalence principle equals general covariance. And that result is what causes gravitational attraction. The idea is that gravity is essentially indistinguishable from acceleration. Thus, for the speed of light to remain a constant for all observers, spacetime must be variable, and that manifests as mass being attractive to other mass. General covariance is sometimes called diffeomorphism invariance because of its close relation to it. But the two are actually different concepts. Diffeomorphism invariance refers to the idea that coordinates have no physical meaning and that all coordinate choices are arbitrary distinctions. The idea is that the physics of the system being described is not affected by the choice of coordinates. Let's do a simulation using Einstein's universe without lambda. So you choose some set of coordinates somewhere on the other side of the universe. I'm going to choose a set of coordinates in the complete opposite direction. We both perturb our universes in an arbitrary location and press play. Both of us will see our universe as collapsing to a single point in the center of our chosen coordinates. But which universe is true? What does this mean? It is as if the universe is collapsing towards all points, which is exactly how gravity works today. So this simple argument is enough to call the collapse interpretation into question, which eliminates the need for a cosmological constant. Modeling the entire universe with general relativity is already a questionable endeavor in the first place. Something is troubling about academia's acceptance of these rudimentary models. Both the Einstein universe and the FLRW metric are gross simplifications that do not match reality. There is little reason to believe that these types of solutions make any predictions at all. In fact, the FLRW makes exactly 0 predictions. Some argue that the scale factor helps determine the evolution of the expansion itself, but this is not a prediction. Any prediction made by the FLRW is a prediction of the chosen starting parameters, and the equations can accommodate a wide range of options, which include collapse, expansion, and everything in between. Einstein himself cautioned against such ad hoc repairs. In 1931, he wrote that resurrecting lambda merely to force agreement with stellar age estimates was no more justified than its original introduction, and that he would have preferred to abandon relativistic cosmology altogether rather than reinstate lambda. Expansion is the collapse problem in reverse. The term vacuum is intended to represent the absence of things. In Latin, vacuous derives from vacuotus. Vacuitous. I think it's vacuitous, meaning empty, the void, emptiness, nothing, or simply space. They're all referencing the same phenomenon, or rather, a lack of phenomena. In physics, the meter is defined as the distance that light travels in 1 divided by 299,792,458 of a second. Space is how we quantify emptiness. Spacetime is an additional term that references the 4-dimensional analog to space. It's the same thing, it's just space with time. In general relativity, spacetime is a 4-dimensional manifold and a metric tensor g mu nu. The question of whether spacetime represents a real physical substance is still up for grabs in the mainstream. The substantivalists argue that spacetime is made up of particles or a field, just like all physical objects. The relationalists argue that everything can be ascribed to the relationships between real physical objects. And while many phenomena suggest that spacetime is a real physical substance, all of them can be described without a physical spacetime. Curvature, gravitational lensing, frame dragging, and black holes can all exist in a relational framework. Curvature is encoded in the Riemann curvature tensor, which describes how geodesics deviate relative to each other. Spacetime is often asserted to be real by physicists, but the claim has no theoretical, mathematical, or physical backing. It is simply an assertion based on their interpretation of curvature. Curvature is a very commonly used word when discussing gravity, but curvature itself is a misnomer. In fact, there are two hidden meanings in the term spacetime curvature, and both of which are wrong. One type of curvature is typically paired with the bowling ball on a trampoline analogy. The other has to do with the nonlinear nature of relativity. In reality, both meanings refer to the same phenomenon, the tensors in the field equations that describe the relationships between real physical objects. The curvature is a reference to the symmetrical nature of the tensors involved. Stars and planets are round because gravity manifests symmetrically. The distance from 1 meter to the next varies because of the interplay between the stress energy tensor, which encodes the mass and energy, and the Einstein tensor, which encodes how those quantities shape the metric of spacetime. In other words, mass and energy are the nouns in the tensors, and time and distance are properties of those nouns. General relativity allows us to choose any set of coordinates. In fact, diffeomorphic invariance forces the laws of physics to be invariant under arbitrary, smooth coordinate transformations. It means that the form of the physical laws, the equations, does not depend on our choice of coordinates. What matters are the relationships between events, not the coordinates assigned to them. In other words, curvature of spacetime happens because of a coordinate choice. We are free to shift coordinates however we like, so we can always remove apparent curvature in a small enough region, or add to it. This shows that curvature is not an intrinsic property of spacetime. It is a description of how relationships between physical quantities vary. None of the arguments presented in the following pages hinge directly on this ontological perspective. You're free to believe that spacetime is a real physical thing, even if you find all of my other arguments convincing. However, this one intuitive proposal is what ties everything else together. Spacetime is best described as the absence of physical things. It is how we quantify variations in mass energy density, but it is only a numbering system. In truth, this is already known by all experts. Everything I'm trying to say here is simply that mass and energy are ubiquitous. There is no such thing as absolute zero or a perfect vacuum. It is entirely possible that there are subtle differences between the arguments above and an argument for the lack of a perfect vacuum, but I view those as the same argument. If every location always contains some amount of energy, even quantum fluctuations in the background fields or whatever, then spacetime is never flat. It may turn out that spacetime is a physical entity, perhaps something that overlaps with quantum fields, but based on the laws of physics as we currently understand them, we do not need to treat spacetime as a separate physical thing. The behavior of matter and energy and the relationships between the physical events can be described entirely in terms of their field interactions and coordinate-independent structures. So even if spacetime has an independent existence, it plays no explanatory role that cannot already be accounted for by the relationships of mass and energy themselves. It is not imposed on us by any theoretical or mathematical necessity. space balls. Early models portrayed the atom as a small ball orbiting a larger ball. We now recognize this model as an absurd representation of reality, which is better understood as a probability field surrounding a dense nucleus. Because electrons are governed by wave-like behavior, their exact location is best known as the likelihood of finding an electron, which means there are no clear defined boundaries to atoms. Worse than that, even protons don't have boundaries. On the subatomic scale, protons, neutrons, and electrons are all governed by quantum mechanics. This means they don't have fixed surfaces like balls. Probability distributions define their size. When scientists say a proton has a radius of 0.84 to 0.87 femtometers, they're talking about the effective size it appears to have in scattering experiments. The mass gradually decreases away from the center. There is no edge to it. The current understanding of the proton radius is that it's still a mystery. Period. Measurements of it don't seem to match up from one experiment to the next. This is somewhat expected, but still problematic in physics, as matter is now understood to be a fuzzy, messy, interconnected probability cloud, which means there are no hard limitations to predictions or experiments. Choose a large region of the universe and draw an imaginary boundary around that region. While it is certainly possible to obtain the density for that region by just dividing the total mass by the volume, the distribution of mass and energy within that region is not represented by a single density parameter. The density might contain a large cluster of small galaxies coalescing into a single massive spiral galaxy. If this region were modeled using Einstein's simple approach without a cosmological constant, it would become unstable and collapse. If the region were modeled with the FLRW, the parameters would need to be adjusted so that the structures aren't lost due to expansion. Recent work on the averaging problem strengthens this critique. Brown, Lotta, and Coley write, "The cosmological back reaction from perturbations is clearly gauge dependent and obviously depends on the choice of averaged Hubble rate. The need to pick a gauge and a Hubble rate means that any conclusions will be arbitrary and dependent on the choices you made. In one common gauge, the effect can be arbitrarily large, and if you adopt a very small smoothing scale, while in another gauge, it disappears entirely. The magnitude of back reaction is not a firm physical prediction, but a mathematical artifact."